The earth beneath our feet is mysterious. But we know one thing for sure. It's hot. In this mine, 1.5 kilometres deep, the rock temperature is over 50 degrees C. Without powerful air conditioning, you don't last long. If you could dig deeper, it would not only get very hot, it would get very strange. You might think the rocks would eventually be molten, but they're not. This is strange because the temperatures deeper down are certainly high enough to melt rock, thousands of degrees. And molten rock is what comes out of volcanoes. It seems we're living on a cool but very thin layer of ground just above a red-hot mystery. What exactly is inside the Earth?
Well, it would be good if we could just dig down and find out, but to dig a hole more than 6 kilometres, it's beyond our technology. The drill bit starts to melt for a start. We have to find other ways, like studying the rocks from volcanoes. This is volcanic basalt. It used to be molten lava. Now, this piece of rock is heavier than most other rocks, and that's the first clue about the rock down there. It's heavy.
Earthquake. Buildings crash down. Somewhere underground, the rock has suddenly shifted and powerful waves shoot through the ground. But as well as creating great damage, earthquakes do something you might not expect. Earthquake waves are strong enough to travel huge distances, not only on the surface, but right through the Earth. Collected as seismograph records, they offer clues about what is deep underground. As well as travelling through the crust, earthquake waves, or seismic waves, also follow deeper paths. These paths reveal that the rocks are not molten, but soft. They seem to be soft in the same way that red-hot steel is softer and more bendable than cold steel. That's why a steel rolling mill heats it in a furnace. Hot rock deep down seems to be much like this. Yet from a volcano, rock often comes out as lava. Flowing lava proves that rocks really are hot enough to melt. So what's going on?
If you've ever tried to pick up a big hunk of rock, you'll feel the answer. It's heavy. Now, imagine being underneath kilometres of this stuff. The pressure is incredible. The force is so much it stops the rock from melting, even though it's very hot. Pressure alone keeps the rock solid. Near the surface, the pressure is less. And with the pressure off, it melts. This explains why lava is liquid. But deep underground, the picture is of solid rock, very hot, and the force is so much it keeps the rock as solid as red-hot steel.
So is the inside of the Earth all made of hot, solid rock? Once again, seismic waves reveal clues to what we cannot see. When they go right through the middle of our planet, they trace strange paths and reveal something else. The Earth has a core. So the main layers in the Earth are 1, the crust, which we know a lot about, 2, the hot solid rock beneath, thousands of kilometres thick, called the mantle, and 3, the core. Of course, the next question is, what's in the core?
Well, figuring that out is another piece of detective work. Here are the clues. 1, we take a device like this, which is called a Cavendish balance, and we measure the force of gravity. From this, we're able to work out how much the Earth weighs. Now, the Earth weighs 6,600 billion tonnes, but you don't need to remember that. All you need to remember is that the Earth is extremely heavy. 2, we know how much rock weighs, and we know how big the Earth is, so we do our sums, and we work out how much the Earth would weigh if it were all made of rock. But the Earth is twice as heavy as it should be if it was all made of rock.
This suggests that the core must be much heavier than rock. So what then is the core made of?
Here's the next clue. Anyone that's ever seen a magnetic compass would know that the Earth has a magnetic field. It keeps the compass needle pointing towards the North Pole at all times. Now, magnets are made from iron and nickel. Plus, iron weighs a lot more than rock. Believe me, this piece of iron weighs a lot more than the same sized piece of rock. So, what if the Earth's core was made from iron? It would help explain two things. One, the magnetism of the Earth, and two, the weight of the Earth. We think the Earth's core is mostly made from iron.
It's a conclusion which is helped by the fact that meteors and asteroids are often also made of iron. Lots of iron meteorites like this one would have been floating around when the Earth was forming. Maybe this is where the iron in the core came from. But not a lot else is known about the core. For example, although we know that it is the hottest part of the Earth, we don't exactly know how hot it is. On the other hand, we do know that within the core is a hard inner core and a molten outer layer. Indeed, this outer core layer is thought to be the only truly liquid layer inside the Earth. Here we have a situation where over billions of years, the heaviest material, iron, has sunk to the centre, overlaid by less heavy material of the rocky mantle about 3,000 kilometres thick, and topped by a thin skin of crust rocks, which are least heavy of all. The crust is, of course, cool at the surface. From the core, heat spreads outwards. This heat, we think, causes the mantle to sluggishly shift and move around in huge, slow currents. What that movement might look like is actually not hard to imagine. The boiling up of clouds through the air is probably very similar. Of course, with rock pushing through rock, it takes much, much longer, perhaps millions of years.
If you've ever watched one of these lava lamps before, you'll have seen something else just like it. The globe at the bottom here is heating the lamp. If this was the mantle, these would be huge plumes of super hot rock forcing their way to the top. Then, as they cool, they slowly sink back down again. Of course, you have to imagine this millions of times bigger and slower. This is wax in water. But in the Earth, it's super hot rock moving inside other hot rock. And as we've said, the mantle isn't liquid but semi-solid, so it takes a long time. Of course, when a plume hits the surface, that's when we get a volcano.
The huge lifting force of a plume of superhot rock can split the crust and pour out molten lava. If it comes directly up from the mantle, it's very runny, so the volcano does not build itself up high. It oozes. It doesn't explode. However, lava can be made from melted crustal rocks. These often contain water and gas, and the result is very different. The volcano is like a shaken bottle of soft drink blowing its cap. The blast shoots rock and dust high into the atmosphere. These volcanoes are the most dangerous. The well-known cone shape of a volcano comes about as repeated eruptions spill more and more ash or lava around the crater. It slowly builds up around the vent. Underneath is the pool of melted rock called magma. It's called magma when it's underground and lava when it comes out. As the plume sends up new magma into the pool, the volcano may erupt again and again over thousands of years. In between eruptions, it may stay quiet, perhaps for centuries. So people may be lulled into a false sense of security because they can't remember any eruptions. The most famous example of people being caught this way was the ancient Roman city of Pompeii. Built next to the so-called dead volcano Vesuvius, all this was buried when Vesuvius blew its top in the year 79. Many people were buried alive. They had no understanding of volcanoes. On the other hand, the magma may not reach the surface. It may simply heat up the rocks around it and boil the groundwater. The result is hot pools or jets of steam and water called geysers. And it's possible that the magma may be cut off from its plume completely and slowly cool and harden underground. Over time, with erosion and uplift, it may at last be uncovered. These rocks were formed from slow-cooling magma that froze solid amongst the other rocks of the crust. When they finally showed at ground level, their heat was long gone. In fact, all the mountains and hills on the face of the Earth would have been worn down to nothing long ago, unless they were constantly being pushed up again by the power of the Earth's heat. Although volcanoes and earthquakes are sudden and violent, much of the movement of the rocks is very slow, taking millions of years to raise a coastline out of the sea or to lift a mountain range. It's a process that's been going on for billions of years. So it's only fair to ask, how has the Earth managed to keep hot for all this time?
We don't know for sure. We think the early Earth was very hot as asteroids and comets slammed into it in great numbers. So it's easy to understand how it started out hot. Since then, it's had 4.5 billion years to cool down, but it still seems very active. One suggestion is that heat is being created in the Earth through radioactivity. This is uranium ore. We dig it up all the time as fuel for nuclear power. As we can see by the radiation detector, it certainly is putting out energy. Radioactive substances like this are putting out heat all the time. But the question is, how much? Is it enough? I find it really interesting that the bottom line to all geology, the Earth's heat, still has a question mark over it.
So our planet, which looks from space to be such a cool blue, is really very hot inside. The locations of volcanoes and earthquakes make an interesting pattern around the Earth, which at first was yet another puzzle. Why should there be a ring of fire, for example, around the Pacific Ocean? An answer came in the study of oceans. Driven by the heat within, oceans widen, continents move, and the whole map of the world turns out to be changing all the time. The fires below certainly have the power to alter our lives, but in time they will change the whole face of the planet.
For a custom copy of this program, contact ABC Commercial on 1300 650 587 or visit abc.net.au/program sales.